recording? Yes, I'm recording. Okay, so hi, my name is David and I'm with the Hong Kong Polytechnic University, and I'm going to share my work that I've been doing on manipulation of deformable objects. Today I'm specifically going to discuss on various shape representation methods that we have been developing recently. So my research is mostly on manipulation. I use vision as the main perception modality. In my group, we use 3D vision, 2D vision to do various types of tasks, not just sub-object manipulation. We have also worked on some different projects related, for example, to dermatology, to industry, inspection. But today, the one I will be sharing with you is the one related to manipulation of soft objects, as we can see in this left-hand side. So, what is the fuss right now about manipulation of soft objects? Quite a hot topic recently, and the way I generally motivate this problem on why it is so challenging compared to, for example, doing manipulation of a rigid object. When we manipulate a rigid object, whether it's with a robotic hand or interaction of various robotic arms or grippers, by definition, the geometry of the rigid object is fixed. You can't really alter its shape. Once you have established a stable grasp, then you only need, in principle, 6 parameters, 6 values to characterize its pose. On the other hand, with deformable or soft objects, that's not entirely true. Depending on the forces that you are applying on this material, its shape is going to change. So we're introducing additional complexity to the problem. We're introducing additional degrees of freedom. How we decide to manage those extra degrees of freedom, how can we control them? On one hand, how can we represent them so that we can control them? How can we quantify it? That's one of the problems that I'm going to be discussing today. Applications, there's so many applications on this, and I really won't extend much on this, as by now all of us know all the potential that being able to exploit these capabilities with robotic systems can bring, whether it's in surgery, manipulating cables, assistive dressing, food, you name it. There's really a lot of potential in this area. All right, so how do I formulate this problem? So I just put it in 2 ways. One is generally like a graphical and a mathematical. The graphical, so we have here a standard conceptual robotic manipulator, which is rigidly grasping a material which is not rigid. We here assume that we can measure somehow the shape of this material. I mean, whatever that means, I'm going to be giving you later on some methods to do it. And the problem is we want to deform this object such that its feedback shape, or such that the shape can reach this desired profile. Mathematically, we can formulate this in terms of the minimization of an error, a very standard quadratic error of what you are measuring, or the way you are quantifying this feedback. The difference between that and your desired target. What we have to design here is the motion profile of your manipulator. So controlling or doing shape control tasks has, as I will put here, 3 main challenges. Challenge number 1, which is the focus on this presentation, is on feedback representation. What do I mean by that? Say we have here our object. So the questions that we can ask is, how can we measure the configuration of this body, given that soft bodies are in principle infinite dimensional systems? We don't have like a finite set of of parameters that we can use for its representation. So the question we ask also is there any way that we can characterize these shapes or these configurations in a compact way? More questions, how detailed such representation needs to be. So some possibilities, which I will be showing, is you can go from the simplest, simply 3D point embedded into the object. You can use, for example, angles. You can use some curves. You can use some contours and some others that I will show today. So this is challenge number one of the bigger problem of self-object manipulation. Challenge number two is something that I here refer to as the motion shape coordination problem. So we can think of I mean, this is one of the reasons why this particular problem is so interesting, because it has a very nice field so that you can bring tools from many different areas. The shape control problem, it can also very nicely be formulated in terms of these transformations among spaces. We have, for example, the motor space. These are the variables that you can control. Graphically, we can represent the motions or the configurations of your manipulator. And then we have the sensor space. This is what you can actually measure, the way you're characterizing your shapes. So the challenge or the problem number two is how can you coordinate motions in these two spaces? Say, for example, this is where you are, this is your measurement, probably you want to reach this point in this vectorial space to some other configuration. What are the motions that you need to do in this side? So this can be framed quite nicely as in the sense of a sensory motor transformation, to which there are many methods that you can actually use to solve it. And challenge number three, quite not so commonly presented, I must here highlight. We have very recently started working on this, is that I have mentioned a couple of times that the configurations of this object, well, the objects are themselves intrinsically infinite dimensional, and many of the representations that we propose are very, very large. I mean, the vectors that we use are quite extensive. When doing or when trying to drive a large feature vector into a target feature vector, say using very traditional servo controls, kinematic control, resolve rate, motion control, the ideal solution will actually be a straight line in this feature space. However, for soft objects, we can't, we don't necessarily have such connectedness of these different configurations. So just simply by driving or attempting to drive the system from one location into another, we might reach, at least numerically, a region that is actually not feasible, that it doesn't have a clear meaning. So planning in these spaces is also a really interesting challenge that this application scenario poses. And there's a lot of work to be done in this direction. These are just some directions that I'm giving. So yeah, back to the issue that I want to discuss in this presentation, which is on representation. So yeah, how do we represent a shape? Do we have a shape sensor? Do we have a standard way to do it? So, and questions, why do we even want to, or why do we need to obtain such quantification of the shape? Well, at least in the work that I've been doing, I'm literally using like systems and signals, like say control techniques. So I'm formulating this problem as a servo control problem, where we need to measure something. You say, for example, on the output signal of your plant, and then we feed it back. We compare it with a reference signal. So in order to establish a controller in this very classical sense, we certainly need to first be able to measure it, to quantify it. So the challenge here is, given something that you are measuring is a geometric a representation, can you obtain a numerical one? These are some of the issues that we need to address. Having such a numerical representation, we can then establish what I here call an explicit shape servo loop. So you measure, whatever method you use, you measure your shape, and then you provide a target. All right, so what are the options? So these are some of the work we've done in the past. We started using very simple approaches for doing so. We use very much inspired by visual servoing, using traditional point-based features, so either using fiducials or texture on your object. And with these points that we measure, we can then construct functionals, so feature functionals, which might have some geometric meaning. For example, centroids, distances, angles, lines, curvatures, I don't know, you name it. So here it is, we have very standard definitions, and let's see directly the results that we have. So yeah, I mean, these are, I mean, let's just be clear here. So with this kind of representations, we can certainly achieve very simple shapes or very simple results, which is not that bad, from a control theoretic point of view, because we're simplifying or abstracting the very complex representation of it. However, the part that I want to emphasize here is that with this approach to do it, this is what I here call, it is hard-coded. Say, once you define what your feature is going to be, or what your shape representation needs to do, there's no way your method can change it. Say, if you are measuring curvature, the curvature is coded into your system, and you will only be able to measure curvatures or angles or whatever it is. So this is certainly one of the drawbacks of this, probably the major drawback, that is, once you define it, there's no way you can change it. So it's very specific for the task. Now, all right, yes, as I mentioned, I think I put it as challenge number 2. So once we quantify the shape, we need to solve the shape motion coordination problem. How can we do that? There's so many ways, actually. You can use, now so common and popular, you can use neural networks, you can use many sorts of estimators, traditional Broyden algorithms. In the case of many of the works I've done, I'm using a very standard gradient descent rule based on differential motions. It has worked for this work that I've done. It doesn't estimate globally any deformation or shape deformation model. It always locally updates the model, and as the robot configuration and the shape configuration evolve, you kind of forget everything that it was in the past. So it's only local. So I just hear, but anyway, this is not really my scope in this very brief talk. There's so many ways that you can do it, and everyone is free to try the one they like the most. So yeah, so after the first one that I showed, which is the hard-coded approach of using points to define geometric quantities, we started working on a more general way to represent and to characterize these shapes, so that we could do control. And then we work with this method that we here called the Fourier-based features. We're simply using Fourier series, actually, to finite Fourier series, because we limit the number of harmonics to, well, this is up to the designer. I mean, you can use 5 harmonics, or I don't know, something not too large. It generally works okay for many of the shapes that we have. But the issue here is that with this, no matter if you are, as in the case of this figure, manipulating a phantom tissue, or you have I don't know, some spongy or some other type of object, you're not predefining your system to do a particular task, but rather the system will, or the shape descriptor will create the appropriate representation for what it's observing. So yeah, so how do we do this? So we just use a standard Fourier series, and then these Fourier series have nice properties because we can then linearly parameterize it in terms of things we can measure, as in a regression-like matrix, and in a vector of coefficients, which here in this work we use it as the quasi-shape measurement. Literally, we're using the shape of the Fourier coefficients now as the shape feature vector. So the Fourier coefficients become our measurement. And yeah, I mean, the details of this is quite straightforward. We obtain an image, we obtain several points of along the contour. We then we applied a regression to calculate at every iteration what the shape or the Fourier coefficients are that describe the figure that you obtain over here. And this is the way I'm gonna call it, we measure, we represent shape. So it is this vector, which again physically represents the Fourier coefficients, the one we actually feed into the controller. So more overview of this, of the idea. So given a contour, this is a contour in, say, 2D space. You can always project it in terms of this is, for example, at the psi contour, you can project there in terms of the psi Fourier coefficients using simply the pseudo inverse as we present before. And with this, we can use an online adaptive interaction matrix to do control. So if you see this control law, is very similar to the ones we use in standard visual servoing, not just visual servoing, kinematically controlled manipulators. Because the way we framed this problem was as a servo control problem. There are other very nice work over there right now being done, but they don't necessarily need to do or implement their motion controller in this way. Okay, so yeah, just some results. We use this 2D, XY stage platform to automatically deform some phantom tissues into some desired contours. And again, yeah, what we use for this method is Fourier coefficients. We're providing desired contours, which we then project into desired Fourier coefficients, and then we just compute an error over there. All right, so what else we have? Yeah, so more on representation, which is what I want to discuss today. We have very recently, this is what we have currently, this preprint, which is available in our lab's website. We are using now different, this is also general, I mean, same as Fourier coefficients, which are general for generic objects, not just objects, generic representations of shapes. There are other alternatives. We also start exploring by using NURBS and Bezier features. For also, this is for 2D motions using cables. Cables is also very hot right now. A lot of people are doing work with cables. So what these particular curve representation have is they also have, we can also apply, the trick that we did with the Fourier representation. We can decompose the contour in terms of a known, say, sensor-based matrix or regression-like matrix, and in terms of unknown parameters, which we, again, will use as a proxy for shape. So that will be our feedback representation. For both of them, we can use it, either Bezier and either NURBS. We can then compute these coefficients or shape parameters in real time by solving this least square problem. And yeah, here we see some videos where we automatically bend some cable into the side configurations. And more general approaches. So, I mean, so I really wanted to start developing representations that are not so narrow as the one we did some years ago based on, for example, angles based on curvature. So which once you define it as that, there's no other way you can do something, some other type of task. It will only represent that. So another general approach that we recently started working was, this is some work we did in collaboration with the University of Montpellier, with my colleagues Ji-Hon Chu and Andrea Cherubini. We use a principal component analysis for representing, for obtaining a representation of the shape. So how do we do it here? So we have here, let's just go a little bit starting from this graphical representation. So let us here consider this is the robot space. We move in various directions, which result in various contours that we can measure. And what we are trying here to do is, from these contours, from this observation data, we want to obtain the feature vector. So the way we do it is by creating or performing an eigen decomposition of a set of observation data. So we collect several contours around. In this work, we actually did it kind of locally, just around the current configuration, and then we decompose it in standard singular value decomposition. We obtain eigenvectors. Here, the key is that we don't take the whole eigenvector matrix. We just select the first k-dimensional eigenvectors, which will, well, it's arbitrary. We can decide how many features do you want to have. Say, maybe your data has like a dimension of, let's say, 20, but you only have like maybe 6 controllable input degrees of freedom from your robot. So you could, so that you can prove analytically convergence of your feature, feedback features, you could select maybe three eigenvectors from your decomposition. So we use the first 3 rows of the eigenvector matrix, and then we project the real-time contours. This is a real-time contour, just minus the bias. This tilde means not the bias, the average vector of your data set. So we project the real-time measurements of your contour, and by using these eigenvectors, and it will, well, what it will mean geometrically is that is projected into a subspace of this eigendecomposition. So the dimension of this S vector will be, depending on the number of eigenvectors that you are actually selecting. If in case 3, that you will only represent with 3 numbers your shape. So of course, having very few numbers, you will lose some information. It won't be the same to have the full data set which is representing a very complex contour, and only having 3 numbers, it will be a very rough representation. So we did some experiments. This is again it was done in Montpellier by Ji-Hon. And some of the interesting things is that for these, we actually use it for representing both. We represented deformable objects and also rigid objects, as we can see in this little video. We did, so yeah, here it is. We did rigid object manipulation. Not because, this method is intended to replace existing rigid object visually guided manipulation methods, but is only to demonstrate the generality that it has. So as I mentioned, this will try to obtain a representation of whatever, either the form of logic or rigid object that you're providing, and it will give you some values that you're deciding to use. Yeah, I think I need to move on. All right, so this is the very last one we start doing. Some might even ask, so if you're using PCA, which in general PCA, you need to collect data first, and then you do the projection into the subspace. Why don't you use autoencoder, which is as we know, some very similar way as what the result the PCA provides, and which actually we did. So we train an autoencoder network, and we use, in this case, the bottleneck layer, which is, the code, which is a reduced space of your original data. We use that as the representation for the object. This is what we feed into the controller. This is your measurement. This is, in the control system diagram that I presented in the beginning. This is the one you're actually feeding and comparing to the reference. So yeah, compared to standard PCA, autoencoder has continuous adaptation capability. So even if you don't really need to collect all the data, you can start doing that on the fly. However, one of the disadvantages that we found is that it doesn't provide orthogonal feature codings. No, we didn't find out. We know that that's one of the characteristics of autoencoder. And yeah, well, this is some work that we also have in pre-print. We have it in a lab website, and we tested with a 2-arm manipulator. And yeah, I really need to conclude. We model the shape servoing problem as, we model the control of shapes as a visual servoing problem. That's the way we're solving this issue. And we have proposed various shape feature representation methods using points and using contours of objects in 2D and in 3D as well. And we can use online algorithms to estimate the deformation model. Whether you estimate the global model, the local model, there's many ways, and it generally depends on your availability of data, your computation, and your application. And well, we use some controllers to manipulate elastic objects. So we by the end, we do want to do the task, the motion task. So open problem, anyone watching this? Very often in this problem in this field, we don't estimate or even have much knowledge of the mechanical properties of the object. We do the task, we measure geometries, but do we really know the stiffness, say the mechanical properties of this body? In my opinion, this is one of the challenges that we as a community need to solve. I thank you all for for listening to this video. Whoever downloaded, this is my team. You can find some information of our work in this website. So thank you so much. Bye bye.